Okay, we're going over matched pairs t-test. Okay, so this is notebook um, notebook 16. See if I have that right. Notebook 16, yes. So if you want to open that, we can get started. But first, let's talk about what a matched pairs t-test is. And in a matched pairs t-test, the samples are matched to each other in some specific way. And the quintessential matched pairs t-test is pre-test versus post-test design. So you probably know this. You give pre-test, um, and then you have some training, and then you give a post-test to see if there's an improvement, right? If the scores improve from pre to post, okay? And they're matched, right? It's the same person taking the pre-test and the post-test. Also, there are times where we do twin studies, sometimes to see if there's a genetic component to some kind of medical issue. We also can study married couples. So then as opposed to independent samples where you can't simultaneously be in both samples, in matched pairs, there's a matching between the samples. Um, they also do dominant hand versus non-dominant hand reaction times. So there's got to be some specific way that the samples are matched. Okay. And now we have three different kinds of t-tests, right? So the very first one we learned is just the basic t-test, one sample, and the code is just stats.t-test. The two sample t-test, where we're comparing the averages of two groups to each other, the code for that is stats.t-test underscore IND, IND for independent samples. Okay, and now we're learning the matched pairs t-test, and the code is stats.t-test underscore REL, right? And instead of the samples being independent, they're related somehow. They're matched in some way. So t-test underscore REL. So we're going to jump into the notebook here in just a second, and we're going to look at the violent crime rates compared between Georgia and Alabama. And we're going to look at the difference, Georgia minus Alabama, and how are these things paired? Why is this matched pairs? Well, we're going to pair them by the year. In other words, it doesn't make any sense to compare rates in one state in 1970 to rates in the other state in 2010, right? There's a lot of difference if we don't match up year by year. So let's take a look at our notebook. Okay, so I'm going to initialize the code there, and you'll notice that the very first thing they say about this is we're matching by year. Okay, so what are we going to do? We're going to create a table called Georgia, and it's the murder rates from the murder rates data where the state equals Georgia. And we're just selecting two columns, the year and the murder rate. Okay, we're doing the same thing for Alabama. Okay, and then we're putting the two tables together. So we have both Georgia and Alabama. Why do we put them together? Well, so that we could do this plot where we plot both by year. And you can see that unlike football, where we would prefer the Georgia dark blue line to be higher than the Alabama gold line, here we're actually talking about violent crime. And so we would prefer these places where the dark blue line is below the gold. But it does appear that at least for several of the time periods involved, that the murder rate in Georgia was higher. Okay. And notice that we're looking at differences. Why? Well, because there's a matching, right? So we take murder rates from the same year and we subtract Georgia minus Alabama, and we get this range of values. Sometimes it's positive, sometimes it's negative, sometimes it's near zero. But notice that the mean and the median are a little bit positive. They're a little bit greater than zero. And we're doing Georgia minus Alabama, which means on average, it appears that Georgia rates are higher than Alabama rates. Okay. So notice that we're importing scipy.stats. Okay. And so I said it was just stats.ttest underscore REL, but here, because we didn't import something as something, we have the scipy ahead of it. Okay, but it's ttest underscore REL. And notice the first thing we put in is an array, right? Notice we do Georgia.column, and then we do Alabama.column. So first two things, we have to have array data to go in. And this was true for the prior two t-tests. It's true for all the t-tests. We have to have array data. So we're doing .column murder rate for both Alabama and Georgia to get array data to go in. Okay, and then the second thing is that we're doing the first thing, Georgia, minus the second thing. Okay, so it matters which order we put these arrays in, right? Because the computer is doing the first score minus the second. Okay, and so we need to know that. Why? Well, because Georgia minus Alabama, if Georgia is higher, Georgia minus Alabama will be positive, right? And if Georgia is lower, Georgia minus Alabama will be negative. So we need to know what kind of situation we're testing for, which is why I'm emphasizing this first minus second. Okay? So what happens, we get the printout and let's analyze it. Notice that we cut the p-value in half. This again is going to be one of those issues where the standard computer code spits out the two-tailed test p-value. And if we want the one-tailed test p-value, then we're going to have to take the p-value and divide by 2. Okay, which is what you see happening right here. Okay, so let's jump back in to the PowerPoint. Okay, so first notice the hypothesis. So as long as we're talking about Georgia minus Alabama, this is the average, and they're two states near each other in the United States. So the assumption is that the average difference is 0. Okay, if there's, a high murder rate in Georgia, maybe there's a high murder rate in Alabama for that year. Okay, so the difference is 0 is our null hypothesis. And why are we doing greater than 0? Well, unfortunately, from the graphics we looked at, it does appear that we should check to see if there is a significant difference and to see if Georgia has a murder rate over the time period that is significantly greater than Alabama. Okay, so that's the hypothesis we're taking a look at. Sorry. Okay. So the code, right? We're going to do stats.ttest_rel. Do the first one. We showed this on the code. All right, we've already done this. First minus second, right? Which is why we're doing mu greater than 0. We expect for Georgia minus Alabama to be positive, right? So we're doing GA, the first minus the second. So GA minus AL. And we're checking to see if that's positive. Why? Because if the first one is greater than the second one, we'll have a positive number. All right. Okay. And when we do that, we get a test statistic of 3.3476 and a p-value of 0.0017. And since p is less than alpha, again, we always use the standard 0.05. If it's not given to us, we're going to reject the null. And evidence suggests for the time period that we were looking at, the murder rates were higher on average in Georgia than they were in Alabama. Before we move on to example 2, I got this p-value wrong. I copy-pasted it incorrectly. So this p-value that we got on the other page, I just double-checked because it felt wrong to me, is 0.0345. Now that 5 is rounded, but to match the p-value we actually got on the other page, here is the actual p-value that we got when we divided by 2, and that is less than 0.05. Which is our standard alpha. So I got the reporting out correct, except this p-value I recorded incorrectly, and I apologize for that. So let's take a look at the second example. Okay, so here we have a pretest versus post-test situation. And why would we compare murder rates in 1971 to those in 1973? And I put mu sub g to see if there's a gain. Is there a gain um, in the murder rates in the U.S. From 71 to 73? Why? Well, the notebook explains that there was a Supreme Court case in 1972 that outlawed, yes, outlawed the use of the death penalty in all 50 states. So the U.S. Supreme Court said no more death penalty. Now, they they didn't say it could never be used. They said that the way it was currently being used was unlawful, and so some states have, in fact, since 72, gone back and reinstituted the death penalty in what the Supreme Court, U.S. Supreme Court, considers a lawful way. Um, but in 1972, all death penalties in all the states went away. They were said, nope, you can't use them. And so the question is, well, some people, and I don't want to get into a big political debate, but some people say, hey, maybe the death penalty is a deterrent. And if it's a deterrent and it went away, then maybe there was an increase. Maybe the murder rates increased because the deterrent went away in 1972. So can we compare the 1971 numbers to the 1973 numbers? Okay, well, maybe we can. And again, we're going to use the t-test rel, stats.t-test underscore rel, and notice that we're going to do 73 minus 71. Why? Well, we always do post minus pre. Why? Well, because if there's a gain, if there's an increase, then post minus pre will be positive. So we're looking for an increase. Now, honestly, if we do pre-test versus post-test and we're helping runners train for a race, we want the post-test scores to be lower. We want the times that it takes them to complete the race to be lower. Okay, so you have to think carefully in pre-test versus post-test what actually is an improvement. Usually it's an increase, but often it's a decrease. Okay, so let's take a look at how to do this. All right, so we're going to match by years. And so you see that we're in the murder rates table where year is 71, sorting by state, and getting the murder rate. Okay, so we're also doing the same thing for 73. Year is 73, sort by state. Why are we sorting by state? Well, that way we're matching the pairs so that when we do the subtraction here, we're subtracting Georgia 73 minus Georgia 71, or Minnesota 73 minus Minnesota 71. Okay, and when we run this, right, and notice that we use dot columns, so these are arrays. So we've created in 73 is an array, in 71 is an array. So when we put them in here, we are putting two arrays in, and we are doing the 73 data minus the 71 data. Okay, and what do we get? We get the test statistic of around 2.78 and a p-value of 0.0077. Okay, let's jump back to the slides here and see. So we do have the p-value correct this time. Okay, and do we need to cut it in half? We can. Certainly, it's a one-tailed test, so we can cut the p-value in half, but do we need to? Nah. The 0.0077 is less than alpha, less than 0.05, so we reject the null, and evidence suggests that murder rates did increase from 1971 to 1973. So some people who believe that the death penalty was a deterrent might claim this is evidence. There are arguments on the other side, which is why I don't want to get into a political debate, but people who don't believe the death penalty is a deterrent might have something to say about this. And again, it's just a really interesting political debate, and we have some statistics and data science that can apply to that people could use for that purpose. Okay, so what's our next example? The question is, when a man and a woman are in a relationship, does the man tend to be older? Okay, how are we going to answer that? And this is the rest of the differences by state. This is a box plot showing the differences by state between 71 and 73. And by the way, Um, there are some states that did not have the death penalty. And if you throw those out, the p-value is even a little bit lower. Okay, so it turns out that even when you throw away these sort of these states that don't matter as much, right? Because if they didn't have the death penalty in 71, then there was no change from 71 to 73. So if you throw out the 6 states where there was no change, we still in fact get a small p-value and we would reject the null. All right, so jumping into the age example, we're using this first day surveys, and mother's age and father's age, sorry, are over here. Okay. And so we read the data in, and then notice we do survey.column mother age and then survey.column father age. Why? Well, remember, it's always first minus second. So here they're doing mother age minus father age. And if you recall, we had a less than. Why? Because it's always the first array that we put in minus the second. That's how the computer handles the subtractions. Okay, and if the males are older, the females are younger, um, then the difference would be negative, right? If the mother were, you know, see, these are college kids. So let's say if the mother were 38 and the father were 40, and I did that subtraction, I'd get a -2. I'd get a number less than 0 if the father in fact was older. So that's what we're checking. We're checking to see this alternative hypothesis is checking to see if in fact the men are older. And as you can see, when we run that, we get a p-value 3.96 times 10 to the -7th, so it's very small. And we'll take a look at the box plot in just a moment. Jumping back, all right, so our p-value is 3.96 times 10 to the -7th, and that's really close to 0. Really, 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 really close to 0, which is less than our alpha, which is they didn't really specify, so let's say 0.05. Since p is less than alpha, we reject the null, which means we have evidence for the alternative hypothesis. And like we've been saying, the alternative hypothesis is that in fact the males in the relationship are older than their female partners. Okay, so it's not just an association now. Now we have some scientific evidence that that difference is significant. Okay, and now here they're actually just showing us, hey, what is the age difference? And it turns out that the males appear on average to be about 2 years older, 2 years and a month older. And then this is showing the age differences in a box plot. And while there are some outliers, there's a lot of different differences. There's a lot of variation in human beings. It does turn out that the median and the mean on average do appear to be positive. And the age difference is father age minus mother age. So we've kind of switched there. But you can see that the difference father minus mother is positive, so we would expect the fathers to be older. And then the sandwich example. Okay, this is our last example, and what they're going to do is we're going to have 10 people who are raters. They're going to rate the sandwiches. And so these 10 people eat a sandwich from each restaurant and rate them. And usually what we do when we're doing this type of thing is half the group will get the JJ's sandwich first, and the other half will get the Wirehouse sandwich first. So we try to reduce some of the bias. Maybe the raters would score the first sandwich higher, or whatever. But to reduce that bias, we switch them so that half the group tastes one sandwich first, and the other half tastes the other sandwich first. Okay, so the null hypothesis, hey, there's no difference. They're both, restaurant chains, and they both have sandwiches. Maybe one of them's not better. Maybe they're just about the same. Okay. And then the question is, one of them's better. Let's see what we're looking at. So we're looking at JJ minus WH. And if we're looking at this to be negative, why are we assuming that the Wirehouse sandwiches are better? So let's take a look at what we've got. So here we have the raters, and the sandwiches and their ratings, and you can see better here in the table what's going on. Okay, and when we run the stats.test_rel with JJ minus Wirehouse, right? So always first minus second when we put it into this function, we get a p-value that's very small. Okay, interesting. And since we get this small p-value, then when we're reporting out, p is less than alpha, so we reject the null, right? Why do we reject the null? Remember, the p-value is approximately the probability that the null hypothesis is true. Now, there are a couple of assumptions. As long as the data meet the assumptions of the test that we're running, this is true. The p-value is approximately the probability that the null is true. Well, if the p-value is really small, specifically less than alpha, we're saying, hey, let's reject the null because it's unlikely to be true, very unlikely to be true. That means we have evidence for the alternative, which is that JJ minus WH, right? So remember, we're taking these scores and doing JJ minus WH, and we're getting a number that's less than 0. What does that mean? That means that the Wirehouse sub scores are higher on average, okay? So that's evidence that Wirehouse has better sandwiches. This is a little bit of paraphrasing, right? We have evidence that the Wirehouse subs were scored higher. Hopefully, if we have the correct 10 people who do have a good palate and do understand what it is to make a good tasting sandwiches, then we might be able to say this. But what we have evidence for is that the Wirehouse ratings were higher. Okay. And this is pretty much all we have. Let's jump back into the table and then wait, what? So this is t-test independent between JJ and Wirehouse subs. And notice with this p-value, we would fail to reject the null. What? So I just want to say that when it is paired data, we have to use the t-test_rel. And it's a much more sensitive test. We want to use it when we can because it's going to produce more precise, more accurate results. Okay, and if we use the two-sample t-test, the t-test_ind on matched pairs data, we get a different p-value, and it's inaccurate because we've used the wrong test. I can't use t-test_ind when the data comes from matched pairs. Okay, and that's what we're talking about here. That's what the notebook is talking about, right? That you can't use independent samples t-test for matched pairs data. All right, and then there's a couple more code cells down below that you can take a look at as you have time.